Okay, first, let me welcome you all to the class. I hope you had a little bit relaxing weekend. We are supposed to have a quiz this week. I said I'm gonna set it up on Tuesday, but I think since I did not officially announce it, I'm gonna make it on Thursday. Okay, that's number one. Number two, ya shabab, with regard to the homework. You are a 308 student. You are not a 307. You are not 203 civil engineering. You are not 201 static. You're not dynamics. You have passed through all of these courses to arrive here. And what happened during the past few days was not pleasant, if I want to say. Student know that this is a coordinated course. And let me explain myself very clearly over here. If this is a coordinated course, it means there are other professors, no matter how many, 1, 2, 3, and there are several, maybe hundreds of students who might, if I give you any special treatment, will not be fair for them. We have received a clear instruction from the coordinator that the homework solution should be submitted at 6 p.m. Right after the submission of the solution by the student. What I didn't do is this. I was afraid that for any reason, maybe there will be an extension or something. So I said to myself, let me not risk it and put a link, an automated link, and maybe I forget about it for the solution. So I said, okay, I'll post it tomorrow, since we don't have the quiz today or the day after. And yes, I didn't post the solution. Be careful. I don't care, and I don't want to know if Dr. Samir Makid or Dr. Fadi posted their solution yet or not. I don't want even to know. What I know is that we're adult, grown up. We have an agreement on the 6 p.m. to be the deadline. Now, I received tons of emails asking me for extension. So I said, what's going on? So I talked to Dr. Fadi, I talked to Dr. Samir, and I told them, is this happening to you? They said, we received 1 or 2 email. Others said, no, I did not receive any email. So I was only the person here who's receiving a lot of emails asking for extension. So I said, okay, good. No extension, fine. I replied to every student. I told them there is no extension. But later, I discovered that one student come and say, okay, that's my solution at 9 p.m. 9 p.m. I said, I forgot. And there is another student who said, I actually thought it's at 12. And this is my solution. And then there is another student who totally submit the homework to a different classroom. So what do you want me to do? What do you want me to do? And then we get into the business of faith. I swear, and now I am in charge here to either make that judgment. When a Muslim swear by Allah, is that accountable? Is it not? I'm gonna tell you this up straight forward, ya shabab. This is too embarrassing. I can't. I mean, it's if it is a quiz, I am in control for the quiz. I would never speak to the president or the chairman or the dean. Actually, they do not allow themselves to speak to me, because they say, we hired you, we put you here in this office, you are in charge. Quiz is yours. Do whatever you want. I do what is rational. If my student said, please, let's delay the quiz, I will do it with a big smile. I have been always cooperative. But if you think that I am going to be cooperative on what is coordinated, and it's supposed to be coordinated. Today, I give you a special treatment. And then, you know what? Let's make the deal here. If you hear from other student in other section that they have been given any special treatment in terms of submission deadline or something, come and talk to me. I am not gonna tolerate that. And I always do. I always speak. If I hear that my student were not treated in good well compared to other, I get so upset. But I can't do this to others. So please, let's end this from today until the end of the term. Don't talk to me. Anything coordinated, don't talk to me. Now, I have to admit that, yeah, maybe if there is a pressure from all students in 308, I hear, Dr. Fadi hears, Dr. Samir hears, everybody said, oh, okay, there is a problem, let's fix it. I understand that, which is fine. You can speak about extension, and Dr. Fadi student can speak about extension, and Dr. Makid student speak about extension, and if we all agree, then it's fine. But sending the solution several hours and then putting that position that, oh, they did not put the solution, by the way, is not acceptable. Do you understand that? So don't blame me, and don't blame anybody else. It's very clear. The homework was assigned a week ago. 1 week ago. I'm gonna tell you one thing. I'm not trying to give you excuses because of my actions. I'm trying to be, oh, don't blame me. I am very kind. I don't care if you think of me as a kind or not. This isn't how life works. So, believe it or not, if you are in a job and you did that, your boss is never gonna let it go, especially if he doesn't like you. Especially. And if you think that you are gonna work on a workplace where all the walls are painted in pink and it's all about love, you're wrong. There are too many people who doesn't like you and who will not like you. And there is no place for mistakes. And yeah, you may not get fired, but the next time you may. So think of this as a way for discipline, teaching you how to become disciplined. And by the way, I visited many companies during the summer, many times. I drove myself from one company to another. And the first comment I know, I heard it. I was so surprised. I said, that's too funny. And they said to me, I told them, how is my club student here doing? And they said, I don't know, how do you do it? But the guys report at 8. They come at 8. We have students from other university. They never make it at time, never. Your student always make it at time, unless, 1 or 2 days. And I told them, I think we don't realize it. The student do not realize it, all of us. But this 5 years of continuous attendance, discipline, it makes you a good person later. They love you. Believe it or not, that's the true story here. So I hope you got my message. Let's get back to business. Now, what did we talk about last time was the conjugate action. We said that the conjugate action is the sort of action by which, if we have two components, a drive and a driven, a gear, an opinion, and so on, come in contact with each other, then if this is the point of contact at a given point of time, then somebody can construct a tangent, which is very reasonable, to curvature in contact. Then you draw the tangent, and by plotting constructing the vertical line to that tangent, a perpendicular line to that tangent, the point which is intersecting the center is called P, which is the pitch point. And what we said is that a conjugate action is satisfied when the next time, you know, they move, they touch each other for a while, and then they leave. So let's say the second point is here, the next second. So we said that this conjugate action is guaranteed if the tangent, which could be right there, is constructed, and when we plot the perpendicular line to that tangent at the point of contact, the line will also pass through point P. Now, if the line passes through point B, then we say that this is a conjugate action. Okay? Now, why this is good? Why this is important? Because if we fix the point there, point B, then with respect to the contact point, okay, we will see in gears that basically the angular velocity will be, the ratio of the angular velocity of the two parts will be the same. Now, what does it mean to have a constant angular velocity ratio? What does it mean? Well, if we have a gear which revolve around 1000 RPM, and then there is another one which is 500 RPM. Now, when you put them together, right, and then you switch on the 500, then the 500 produce 1000 on the other side. What do you want? If you put a measuring device, you know, for RPM, and then you put another one there, you should see 500, and there 1000 all the time. Now, what happens if this is not constant? Because the point of contact is changing. Remember, velocity equals to omega r, which means that the omega equals to VR. So if that r from which the rotation is measured is changing with time, then you may have a fluctuating motion, something like a 1000, and then 980, and then 1000, 980, 1000. What is this? What is, how can you maintain the same flow, the same pressure, the same, how? The process is all ruined. You need a smooth, constant motion. 1000, always 1000. So, Involute profile is even way more interesting. It's one of the ways to produce that constant motion, that constant angular velocity. But it is more, I'm gonna put it between two parentheses, more magical. And I'm not joking. It is way more unbelievable. Is that we do not promise only to let the point of this line, which is the perpendicular line of contact, to pass through point B. No, we are actually gonna promise that as the motion is set, the contact point change, but the line of action, this line, is gonna be always constant. Now remember, this line changes here because the tangent changes and the perpendicular changes. However, as they change, they all pass through point B. No, no, no. We want the teeth, as they move to with respect to each other for that period of time of contact, their tangent, even if it changes, it's always on this line, always on this line, always on this line, always on this line. Can you believe this is doable? The curvature of the teeth is not straight, and the point of contact between the two teeth is changing. It's moving here around the profile. So how can you guarantee that? Well, it turns out that this is done through the Involute profile. So what is said here in red, it says in the case of the Involute profile, it will be shown that all point of contact occur, all point of contact, multiple ones, on the same straight line AB, and all normal lines, okay? To the tooth profile at this point contact coincide with the line AB. This is line AB. Look at it. Just to show you. This is line AB. Now, what I want to show you over here is this. I want to show you that we can actually do this. It is not something like a magic, but to show you this, let me tell you how it is done, okay? So imagine that we put a flange, like here, a flange, which is B, like that, okay? On top of this circle, cylinder, okay? Cylinder A. That cylinder A, okay? Don't think about how big it is. What is its radius? Just leave it aside. Now imagine that in this cylinder, we fixed the rope here, and then we wrapped it around it. So we wrap it around it. And now imagine that you are pulling that rope from the top right here. Now, if somebody, or if you fix the rope over here, you can't pull it, right? It will always resist you, which means the rope will stay in tension. Now, while you are pulling the rope, you can raise your hand up, you can lower it down. So for example, if you decide to push your hand down, the rope will wrap around, but it will go like that, right? If you decide to take the rope up, it will go like this. Regardless of how do you change the altitude of your hand, okay, the rope is indeed always tangent to the circle, always, will stay always tangent to it at the point before it's split from the curvature. That's point number one. Point number two is this. If you imagine that you have the rope like here, and then on the rope, you mark a point A. On the rope, you bring the marker, let's say the rope is yellow, you look at point A, and then you put a red marker on the rope. And then what do? You pull, while the rope is in tension, you pull it up, until you see what happened. As you pull it up, you can track the point A trajectory. How does it move? Until it reaches the end of the flange, this flange. We call this one point C. Now, what did happen over here? You made a profile of all trajectories of point A on the rope in a condition that you were changing the rope like this. Do you understand that, ya shabab? So what happened is that this trajectory of point is the involute. And it has, you know, some of the feature that you need to think about is this. This is tangent here to the circle, and also this involute has a curvature. It's a curve, and its radius changes, and it reaches maximum. The maximum radius of curvature is at point C. And because this point is being drawn while you are moving the rope in a curvature, indeed, any line here is going to be also perpendicular to that curvature. So any line you extended from point E is going to be perpendicular to the curvature. Okay?
Doctor,
now, yes.
The involute curvature should connect the two gears?
Well, in reality, you want the teeth to follow the teeth profile to be an involute profile. So you may imagine previously that when you go to the market and you see a spur gear and you look at the teeth, they look like this, you may think that they made them because of, I don't know, something. No. Yes, Ya Ali, these are made based on an involute profile. Yes.
Why did we stop at point C? Why wouldn't, for example, go on further?
Because you can go on. We will see that involute, ya shabab, by the way, it's a mathematical geometry thing. So you can generate involute. There is a process to generate involute profile for any kind of, circle, whatever. And it can go forever, but it's going to become useless because in the end of the day, imagine this way. This is now the circle, the cylinder. You see that? And this one is another cylinder. These cylinders are exactly like this one, but they are different in size. Now, the relation between the cylinder, which we use to generate the involute, is governed. We will talk about it because what we said before, we need to focus on what, ya shabab? The pitch circle. The pitch circle is where the two gears come in contact. So look, the pitch circle is in green right there. The involute is this. Look at it. I'm going to draw it in blue. This is just like this. You see that? And then for the other one is like that. So there is no point to make it bigger and bigger. Why? Because that's it. Now in here, you can, somebody, ya shabab, can imagine that, oh, we now know how to draw the gear. The teeth of the gear should be like this, right? Should be like this. Do you understand? That it's follow the involute. And then the other one goes the same way. You see that? So that's how we use involute profile to generate the surface of the tooth itself. Now, what is important right here, I want to show you, is that is this. These are some fundamentals you need to understand. First of all, this circle that is used to generate the involute, okay, will have a point A and will have another point B for the two mating gears, okay? And at this point, at one point of contact, okay, this line is the pressure line. That's the line which make the pressure angle. Okay, that's number one. Number two, the pressure line will pass through point B. Now, do you remember point B? Point B was here in this example because these are not gears, but in here, it is the point which connect the two centers. That's condition number one. Number two, that point pass through the location where the two gears are touching, which is at the pitch circle. And this line, which is, by the way, tangent to the radius of the involute circle. The involute circle, what do we call it? We call it the base circle. So this is called the base circle. Base circle is the circle we use to generate the involute profile. Now, if you look over here, so we have a lot of dependencies over there. Now, what I want to show you is that, so this is basically what it says. It says that the circle which we use to generate the profile is called the involute or the base circle. So what I'm going to do, I am going to show you something very interesting. So let me share my computer screen over here for a second. No, not now. I need to do something. So let me do this. Now, what is this? This is an animation of an involuted profile gear. And what I want to tell you is the following. Do you see this line, ya shabab? This is the line where the perpendicular, this is the radius of the base circle for this gear. And this line is the radius of the base circle for the other gear. And we said that the action line, do you remember? This point is A, this point is B. Look at it. This is point A, and this one is point B. These are, this line and this line are these one, the one I just made over here. You see this? Now, what do we know? We know if we go back that this line touches, ya shabab, over there at point P. This is the pitch point, right? Where the pitch circle come in contact. Is that right? The pitch circles of the two gears come in contact. And what do we say here? We said that if we follow an involute, a profile, then this is the promise we deliver. We said, okay, this is involute profile. The two gears came in contact. So when they came in contact, that's the point P, okay? And the line of action over there, which is, by the way, sometimes it is called the pressure line, because this is actually, if you draw a horizontal line, this is going to be phi, the pressure angle. So what did we say? We said that this is the line where the forces are applied. This one and this one. So one gear is pushing this side, the other gear is pushing that side. Do you understand? Now I want you to focus very, very carefully. We said that if you follow an involute profile, as the gear move, the point of contact move. Look, it gets further. But be careful, the gear going down, right? Because it is moving. So here, look at the level. This is the level. Then the gear went down. Then the gear went down further. Why? Because of the rotation. We're rotating. Now, the point, Yusuf, do you want to say something? Okay.
Yes, Doctor,
So,
I have a question.
Uh-huh.
On the first picture on the left, there are 3 points of contact through the line.
No, they are not. I know what you are trying to say. This is not a precise drawing, okay? It's not a precise one. This is focusing on what? On the point of contact right there. By the way, we will show you in a minute that there is a rule for contact. So now this is one gear, this is another one. Gear 1 and 2 are in contact, is that right? So you can call this one gear 3 and this one gear 4. Now, the question for you, gear 3 and 4 could be also in contact right there. The question is that possible? Yes. There might be 2 pairs in contact. One of them is just at the beginning. The other one is about to end their journey. Look, these one about to leave each other, because the contact always starts somewhere here and then go like there. So let me, I'm gonna come back to this one later. So what happened? If you measure here the distance, this is how far they are. Then look at this, get further. The point of contact is moving. Then look, it went from here. This is the route until here. So the point moved all the way to there, right? And look, this is the circle, and this circle is what, ya shabab? This is the pitch circle. This is the two circles that come and touch each other, tangent. You understand that? So what is the question right here? What is it? The question is, as that's an involute profile or motion. As the point move, look, that point is moving, but it is always in here. Always there. I don't know how further I can talk to convince you that this is really wow. So let me show you what I wanted to show you, okay? Without further delay. So what you see right here is an animation. I need to switch it on, and I'm gonna let it go for several times. Now look, follow my the mouse cursor. Over there, the gear over there, they got in touch, they move, the point of contact moves, but the line of action is always the blue one. This is amazing, ya shabab. This is going to secure a smooth motion. That's why you don't feel it. You don't feel that tick, 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 tick. It's not like a step motion, right? It's so smooth. And the line, the forces is always acting in the same line, no matter what. And that's what makes it uniform. That's what makes it constant in ratio. Otherwise, you may have a wavy or shaky motion. Do you see that? Now, to answer the other question, let me show you this example. Now, look, this is the line of action. Now, all of a sudden, here, there, the green circle indicate that there is an engagement. Look at the point of contact. It is moving, but with respect to the gear, it is always acting along the line of action. Now, while I was talking, look at this gear over there. There is another one, A, here, got engaged. Now, what does this mean? It means that, look, this gear is gonna finish a journey up to here, right? While the other will finish a journey from here all the way to there. So this is like, if you imagine that the contact for one gear is 1, then this is 1 point something, because this has only a little bit left of it, while the other has a full contact to go. Did you understand? So I'm gonna turn it on. So look, this is now about to finish. Another one will come. Look, there, another one come, and this one. So it is continuous, ya shabab, right? Always there. And the fact that it is acting on the same line makes the reason why the velocity, angular velocity ratio is the same, which is fantastic. And you don't have this jerkiness or like shaky motion because something is one time happening here, so other one happening there. No, always on the same line. This is really, really nice, really nice. So gears have a lot, ya shabab, in them. It's not just like cut teeth and that's so on. I think now you understand how much mathematics and effort you can put to generate this curvature. because this curvature and this curvature will change their radii, will change their tangent at the contact in a way that will always preserve the perpendicular line of action to that tangent, which is pointing exactly at the same line. This is very beautiful. I don't know, I love geometry a lot, and I think this is really, really nice, but it's all up to you. Do you like it or not? Let me, where is, to share my screen now, go back to the slide. Of course, ya shabab, these are fundamentals. Yeah, which means later we will never talk about them. Now you understood the involute, you understood why the motion is the same and so on. So there are many examples on YouTube, in the internet, on how to generate involute. But in general, for a gear, you can imagine that what we are going to do, we are going to split the gear into equal distances, equal arcs, if you want to call them. And then, okay, we take a curvature, you know, a line, and then we say, if we take this, all right, and then we extend it right there, okay, just like what we did. So you have the rope, and then what do you do basically? If you extend the rope at different tangent, which is the following, let's say, so you take the rope, and then when you are at this point, you said, I am not going to continue down, I am going to continue straight, right? Now, and then you go to the next line and you say, when I reach this point, I'm going to go straight. And then you have another one and you say, when I reach this distance, I am going to go there. So this one, this is the point. For this one, this is the point. For the green one, this is the point. And of course, finally, for the red one, you say, when I reach this point, I am going to go straight. Now, what you should know is that how long is this one should be what, ya shabab, should be related to how many arcs are there. So for this, you actually have arc this, 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 this. So you count them as a length, and then you stop at that length. And if you continue to do this in a successive way, you will end up with the curvature, which is this. Because as I said, you can extend these lines forever. But the reason why do you stop here is because how many arc you should go. You understand? So we all know that if we have now a gear like this, and there is another one like this, and they are in contact at this point, instantaneously, as we did with dynamics, instantaneously, when 2 points are in contact, and if we assume that there is no slipping, okay, then the velocity at this point, so V1 is equals to V2. Doesn't make sense, 2 point, okay? 2 gears in space, or 2 parts in space, and they are touching at one point and they are moving together. The velocity of this one at that point and the velocity of this one, that was the same. So if the velocities are the same, then we will end up with omega1 R1 equals to omega2 R2. And that's how we get the ratio, which is omega1 over omega2 equals to R2 over R1. And by skewering that the line of action is constant and the distances between the point and the centers are always the same, then this ratio will always be the same. And if this ratio is the same, the omegas will be also the same. That's the premises. So basically now what we know is that the base circle is down under this is the circle, which is called the base circle, and above it we have the pitch circle. So the question, and of course, as I told you, this is the contact point over here, the pitch point, and we have the pressure angles. So the question is, let me just get rid of the 2 gear, just me keep 1 gear only. And by constructing the point over there, this is the point B, the pitch point. And I know that this is the line of tangent for the other gear. So the other gear is right there, right? I'm not drawing it here. So, and by knowing that this is the pitch circle right there, then the base circle is somewhere down. You will notice that, do you remember point A and B on the base circles? So by looking only at one circle down, okay, which is for 1 gear, the base circle, ya shabab, let's say this is point A, this point over A, and this is point B. Now, we all know that the distance from P to the center is what, ya shabab? Half the pitch diameter. We said that we always represent a gear by a diameter, which is the pitch diameter, right? So it's actually not P, it's actually D. That's the pitch diameter. So half of that is its radius, the pitch radius. So this is R, which is the radius from here all the way to there. Now, clearly, if you look at this, this is R, and if I know, as we agreed, that the point here on the base circle with respect to the pressure line is going to be normal, because this one now is tangent to the base circle. So that point is perpendicular, and now we know that the missing information is here, which is RB. But if I draw the triangle like this, it's going to be, this is 90 degrees. This one is R, which is equal to the pitch diameter divided by 2. And this one is RB. So if I want to know this base circle, the base circle that we use to generate the involute, it is equal to R cosine theta. And it is coming from the relation between RB, R, and the angle, and the angle theta over phi, not theta. Okay. So also, as I would, ya shabab, you want to maybe in your notebook or something, you want to memorize these or write them down. Along the line, we will have several standard relations. So among these relations is the distances for the addendum and dedendum. For example, as a standard ratio, their distances are 1 over b for the addendum and 1.25p for the dedendum. So these relations are brought here, and it's good to take note of them, because in the future you may use them to, especially in design. So if you have any case where there are unknowns, these values become very handy. Now, the last thing is I want to talk about, then I will stop, is what happened. We talked about 2 circular gears. Now, we know in the industry that there are racks. Racks are like this. That's a rack, which is a straight kind of teethed part, which is engaged with a circular gear. So in that case, we imagine that the rack is a gear with an infinite pitch diameter, infinitely large pitch diameter. And here, if you say this is the base pitch for the rack, and it is related to the base, so the base pitch, which is PB, is equal to the circular pitch multiplied by cosine phi. And lastly, يا شباب, what happened if we have a big circular gear and inside it there is a small gear? This is also possible. What you should know is that all of these can, especially this one, I mean, you can still show that the involute profile can be still satisfied, and the constant angular velocity can be also still secured. There is an example I'm not gonna go over it. It's very simple. You can go over it. Next class, ya shabab, we are gonna talk about the contact ratio, which we just talked about, which is the fact that gears have part of them in contact and then another pair is also in contact. Okay, I need to stop here, and I'm gonna take your attendance right now. Okay. يوسف اليوسف
موجود.
العباد
موجود.
حسن
موجود.
عبد الرحمن
موجود.
محمد
Yes.
عبد العزيز
Yes.
احمد دوسري
موجود.
عبد الله
Yes.
خالد
موجود يا دكتور.
مصلح
Yes دكتور.
سعود
Yes.
عبد الله
Yes.
سلمان فارس سهير طارق.
Yes.
طارق, are you here? طارق. مصطفى.
Yes دكتور.
علي.
موجود دكتور.
خالد عتيبي. حسام.
Yes دكتور.
هاشم. هاشم.
Yes.
سلطان.
Yes دكتور.
نايف.
Yes دكتور.
صبحي. محمد.
Yes.
عبد الله سهراني.
Yes.
مشعل.
موجود.
عرفات. مؤيد.
حاضر.
علي. and حسن.
Yes دكتور. أمير.
Okay. Thank you يا شباب.
Doctor,
Yes.
can you send the announcement for the quiz?
Yes, I will. Yes.
المعذرة معليش بس ما سمعت اسمه.
اوكي يا طارق.
يعطيك العافية.